So deep learning. Okay. Any idea, guys?
I think to get the inside of data, like what data can tell us.
Hmm. Okay. So basically, while learning data science, data science, machine learning, deep learning, AI, whatever the things we are trying to learn here, right, in these classes. So we are trying to solve the real-time use cases. Do you guys agree with that? Whatever the use cases, it's not like about only about the prediction or classification. Whatever the use case, okay, mathematical use cases, which are basically the you know really the pain areas of the companies or pain areas for the business. Okay, for example, if I take an example like in industry, okay, in industry, suppose multiple machines are running, they have started the machines, right? And what happens is, because of the deterioration of the machines or different components of the machines, it is like they are likely to fail. Different components are likely to fail, but when they will fail, our production will stop, correct? And we have something called preventive maintenances as specified by the manufacturers, right? Now, for different components, we have been given the preventive maintenance, some guidelines that after this much of RPM, rotations per minute, or say after this many of cycles, you have to do some kind of maintenance for the components or machines, right? Now, it may happen, or it always happens basically, that before the preventive maintenances, your machine is also likely to fail because you are not running those machines as per the guidelines. Your vibration should not increase this much. Your current should not, you know, go beyond some threshold values, right? Your RPM, rotations per minute, should not go beyond some threshold values. So you are not running the machines as per the specifications. It is not possible in real time, right? It's only in idle scenarios. So we use our data science or machine learning or deep learning, whatever you say, all these concepts or some concepts to solve their problems, to predict the failures in machines, right? Now, just take another example of say cycle time estimation. So different products have been are getting manufactured within the same machine, right? So all the products, each and every products will take some time to be manufactured, right? When we input the raw material and till the time when it gets out as a fully product, then it takes some time. But there are different products getting manufactured on the same single line machine. Now, how will you segregate the different products? Like, how different products are taking different amounts of time to be manufactured, right? As a final product, how will you calculate the cycle time of them? Different products, right? That is a problem. That is not a problem of your classification or prediction, but still this is a problem. This is a use case, right? So this kind of use cases also we try to solve. For example, optimization. How will you optimize the route, correct? For traveling salesman problem, or say route optimization we are trying to solve, right? So these are also the problems which comes under a data science or any mathematical problem, right? Which we try to solve them. It's not like every time we have to solve the problem of classification or prediction only. We have to build the models. It's not like that. We have to we have to build some algorithms as well in real time to solve the problems. For example, dynamic threshold, right? So what will be the threshold? For example, a static threshold of some machines. So how will you get those static thresholds? It's not prediction problem, it's not classification problem, it's not image classification problem, nothing. We are not building any model, we are just developing some algorithms. Downsampling problem. For example, if your sensor in any industrial area, if some sensor is generating a lot of data, sampling rate is too high, so that you are not able to store it in your databases. Your database is not compatible to handle those amount of data at a time, per second or per minute, whatever, right? So we have to downsample the data without losing much information. This is also a data science problem, right? Similarly, in the deep learning, so see here in data science or machine learning, deep learning, whatever you say, here we have categorized the problems. Okay, we can solve using machine learning as well. The same problem can also be solved using deep learning as well. Okay, some differences will be there. Okay, so as you have already understood statistics, you should be very good in statistics to learn all these concepts, all these like machine learning, deep learning, NLP, whatever it is. You have to be very good in statistics, the very basic concepts. Don't worry about the machine learning. Whatever the machine learning concepts you have, uh, for example, in machine learning, if I ask you decision tree, or say not decision tree, just say linear regression, very basic thing. What is linear regression? We are just trying to, get the line which will fit my data well. Correct or not, guys? Is this correct?
Yes. Yes.
Yeah. Now to get the line, we need to get the y equals to mx plus c. That's it. Done. As soon as you get this line y equals to mx plus c, you are done. But the problem arises here. You have to get the line of best fit. It means the line which will minimize the errors. Now, what are the errors? Y hat minus y hat minus y squared. These are the errors, squared errors. Why do you take the squared errors? Any guesses? Any guesses, guys? Why do you take the squared errors?
Else it will cancel the negative and
Remove
plus.
negative one.
Negative. Yeah.
So can't I take this y hat minus y mod summation? I can also take that. It will also, uh, I mean,
Also plus or
it will also
minus.
save us. Sorry.
Will give a plus or minus both the signs. If you take square,
No, it will not
then
give plus. I'm taking mod. So if inside the difference between actual value and predicted value is -4, and I'm taking the mod, it will give me 4. If the
But
difference is 4, it will also give me 4. Same thing.
that is not
But
differentiable.
exactly, this guy is not differentiable at x equals to 0. And because of that, we are taking y hat minus y squared term. There are some reasons for it, each and everything, right? Okay. So okay. So this kind. So yeah. So here we are just trying to get the equation to solve the problem. And to get the equation, it's nothing like about the machine learning. What is machine learning? The uses of use of your mathematics. That's it. You use some mathematical concepts. Okay. You use some programming skills, and you use some domain knowledge. That's it. Done. When you have all these three, you are a good data scientist. That's it. Done. So we are calling this machine learning or data science. Okay, it comes under the machine learning only. This is the application of all these concepts. Correct. Similarly, when you talk about the decision tree, nothing else. In decision tree also, we are finding the genius score or entropy or information in whatever it is. Okay, so it is having formula, mathematical formula only, mathematics only. That's it. So you should be very sure about the basics. Okay, and while starting the deep learning, guys, first we will look at introduction. Initially, we will look at the very introduction of the deep learning or machine learning, whatever. We'll see. After that, we'll discuss about descriptors or feature vectors. Okay. After that, we will see how machine learning is different from deep learning. Okay. Now we will learn discriminative or generative models. After that, we will see some challenges in deep learning. Okay. So all these things are planned. And finally, we will look at some feature descriptors. Okay. So these things are planned for today. Okay, not in entire deep learning. So on daily basis, whenever we will meet in the next weekend, we'll see some more concepts. Okay. So now I want to ask you guys, there are two ways of teaching this deep learning. Okay, one is just programmatically. I'll introduce with some use cases. I'll give the programs. Okay, but for each of the programs, whenever I will write something called kernel in the program, kernel equals to 3 cross 3. What is this kernel? You have to understand why we are taking 3 cross 3. Why not 1 cross 1? Why not 5 cross 5? Right? So, to understand all these things, you need to go back to your mathematical concepts. What is this kernel? What are those features? Why we are taking the images? What is 28 cross 28 images? What does it mean in the images 28 cross 28? Right? So all these things can easily be understood by the help of your mathematics. Okay, and that's why we will learn first the very basic concepts for each of the different concepts, each of the different topics. We'll go into the depth of the mathematics. So after we will cover the mathematics, we will go to the programmatically, right? We'll solve the problems. Okay, but first we need to understand those mathematics. These are very essentials. How they are coming from, how we are, extracting the features. How? Okay. Now, what is learning? Okay, learning in machine learning. What is learning? In deep learning, what is learning? We usually see this learning, learning, model training. Model will learn something, but what is this learning first, right? So, can you guys recognize these pictures? What is first thing? Yeah, Taj Mahal. Okay, and this one, Sachin Tendulkar. Exactly. How did you recognize this? I mean,
By seeing the pictures, like we know from
correct, by seeing the pictures.
Yes, we have seen this before.
experience.
Okay, you have seen this before. Suppose you have not seen this before. What will be your answer?
It is a general building, like beautiful building.
Yeah, you can say it is kind of some mahal kind of thing,
Yeah,
because uh, because you are looking at some features like tomb, these kind of things, right? Yeah, so you will not say this is a building, right? This is some kind of ancient architectures, right? So you are looking at the features here. Here also, if you see this picture, if you don't know the Sachin Tendulkar, then you will probably say this is a man, but when he is having some bat, it means he might be some cricketer, correct or no? He might be some cricketer, correct? Before the cricketer, before classifying him into cricketer, you will probably say he's having some this kind of features, short hair, all these things. He's having uh, shirt and trousers, t-shirt and trousers. So this guy looks like man, correct? So based on the features, you are trying to tell something about any images, and these images are nothing but data only for you, for your mind, for your brain. This kind of images are also a data. Similarly, when we pass this information to the computer also processes the information or the data in the same manner as our brain does. Okay, by help of some algorithms, some algos, whether these algos are ML algos or deep learning algos or any other algos or NLP algos, whatever the type of data we provide, they will process the data. These algos are basically responsible, and that algos you are calling it as model after training. You have identified or recognized these pictures by some features or descriptors or descriptions, or by some a priori knowledge. A priori knowledge means someone would have told you that this is a Taj Mahal, or if you have visited the Taj Mahal, then you can easily recognize these pictures. Similarly, for this guy Sachin Tendulkar, okay, someone would have shown you the picture, or you would have seen him somewhere playing the cricket, and you have seen somewhere previously, earlier in the past. And this kind of knowledge is called a priori knowledge, right? Now, what is the origin of machine learning? First, origin of machine learning. So, it lies in very early efforts of understanding the intelligence. Okay, then what is intelligence? Someone will ask you, what is intelligence? Then it all the definitions that I am giving here, all the uh, you know these are the theoretical definitions. Okay, so intelligence can be defined as the ability to comprehend, to understand, and profit from experience. This is intelligence. So machine intelligence, we talk about machine learning, machine intelligence. So ability to comprehend, to understand, and profit from experience. So that's what we do here, right? We comprehend our machine learning algorithms, they understand the data, and after that we will get profit from those learnings. After understanding them on the data, we get some outputs from those models or algorithms, right? Capability to acquire and apply knowledge is called intelligence. Then what is learning? According to this guy, whose name is Plato, he gave some definition. He told that the concept of abstract ideas are known to us as a priori. All the knowledge which we have been shown before in the past, or which we have been told by someone before in the past, are called as a priori knowledge. And the concept of those a priori knowledge or abstract ideas which are which are known to us as a priori knowledge through a mystic connection with the world. He defined the learning by saying that whatever the past experience, whatever the past knowledge we have through a mystic connection with the world is called learning. That's it. He gave something as a proof. So he gave this definition 2300 years ago, not today. Okay. So he gave the proof, like how can a newly born baby easily recognize her mother or father? So it's like some mystic connection with the world. It then gave some other definition. Okay. But now the question arises. He concluded that ability to think is found in a priori knowledge of the concepts. He concluded that. Now, here the thing is, did he miss anything? 2003 years ago, 2300 years ago, did he miss anything? Doesn't mean that we don't learn anything new, because he only said that whatever the priori knowledge we have through some mystic connection with the world, that is called learning. But what happens when we learn new things, something new? According to his definition, we can't learn anything new, right? Whatever we learn is through mystic connections. So his student, who is Aristotle, okay? So he said he criticized his teacher's theory, basically Plato's theory. He criticized, and as it is not taking into account the important aspect, okay, he said that an ability to learn or adapt to changing world is called learning. He gave a new definition of learning by saying that ability to learn or adapt to changing world is called learning. So whatever the a priori knowledge we have, whatever through the mystic connections with the world, whatever the a priori knowledge we have in the past knowledge, okay, whether by shown by someone else or by uh, spoken by someone else, whatever the knowledge, whatever data we have about something, that is learning. That's fine. But in addition to that, when we learn something, it means when we adopt something with the changing world, this also adds to our learning. And that's why he added one more point to his definition. His student. Okay. This is called learning. If you are building AI models, you are working on robotics, and if you don't know what is marginal probability, correct? So basically, if you are working on say decision tree, random forest, deep learning algorithms, and if someone asks you what is Bayes theorem, very basic things, Bayes theorem, and if you are not able to tell, I mean, how this how these are implemented. So what is wrong in these definitions? These definitions are just saying that whatever the previous knowledge we have, that's fine, that's learning. But in addition to that, whatever we are learning new in a changing world, whatever the things, whatever the new concepts we are adopting with the changing world, this is also the learning, right? And that's what we actually do while training the model and all. Whatever the history data we have, right? We learn from something. We learn something. We have something model, machine learning model, say, based on history data. Now, after the history, after it is trained on history data, when we deploy the model and when we retrain the model, why do we retrain the model? Because the new data have come, right? When the new data have come, so we need to retrain the model again on the new data, so that some new concepts, some new features will be same, but pattern might different slightly, and that's why we retrain the models. And that can you relate to this, guys? So these basic definitions are very important to understand something. Okay, it's the part and parcel of your learning, your deep learning, whatever you are learning. Okay, now coming to descriptors or feature vectors. Okay, what are descriptors or feature vectors? I'll show you some image here. Suppose this guy, lion. Okay, now looking at this image, we will think of something. What will think? It has noses, it has mouth, it has different hairs, some shapes, some eyes, all these things. It has some different parts on the body this picture has. Okay, if I zoom in only the eye, one part, this eye. Okay, how we see, we can easily recognize this image as a lion, right? Because our grandma or father or mother said somewhere or sometime that lion looks like this. Suppose lion comes in some different color, again we'll be able to recognize, because we have learned the pattern. Our brain structure, our neurons in the brain have learned the pattern of the lion, how they look like, what will the mouth, how mouth will be looking like, how nose will be looking like, how eyes will be looking like, what is the pattern, what is the shape of the lion, we have already learned. If some white lion comes to you, then you can easily recognize this is a lion but white in color. Similarly, how our computer system works. So this is what our computer sees. Each and every features of the lion, okay, each and every features of the lion will be read as pixel values in the computer, or any image, not only lion. Each and every images, when you show it to the computer, it will read as pixel values. These individual things, individual cells, individual values are nothing but your pixel values. Okay, and these pixel values will differ. Suppose you have selected this eye, you can also select this nose, you can also select this mouth, you can also select this body. Okay, so these are the pixel values. Now, along with these pixel values are telling you that what is the region. It is telling you about the region thing. Region means what? Inside the body, what are the different distribution of different things here? Like eyes. What are the distribution of eyes in terms of pixels? What is the color of eye? shape of eye, right? If similarly, we can also tell something about the boundary. Boundary means what? The shape, right? What is the shape of the image? Okay. Similarly, you can see here these two guys. One is horse, another is zebra. Okay. You can easily recognize these pictures because the zebra has some patterns on its body like this one, some checks pattern stripes on its body. Similarly, horse, it doesn't have anything. It has some some different features, some different colors on its body. But when we remove the body, when we remove the internal, the region part from these two pictures, it will look like this one. Now tell me which one is lion, which one is zebra. Is it easy to differentiate now? Yes or no, guys? No, right? But how our computer system will work here? Okay, these are the questions. We have two types of features here. One is called shape feature. Shape feature means what? This is the shape feature. Sorry, not this one. This is the shape feature. How the shape of the horse is, how the shape of this zebra is. Okay, so one of the features of any image is the shape or boundary. You can also call it as boundary, the external thing. Okay, what is the shape? What is the boundary of some image? Are there any other features possible? Yes, we can have region features like color, texture, okay, intensity, etc. So here in the previous image, we had a color. This region features are different. These region features are different, as well as shape features are different. This is nothing but our shape feature or boundary features. Now I'll come to machine learning versus deep learning. I'll continue this one in detail, but before that, I want to tell you something about machine learning and deep learning. Okay, in machine learning, basically, we have, or suppose not in machine learning or deep learning, just say we have been given some image. Okay, we describe some feature vectors like we used to do in machine learning. You have already done it, right? Different features in the form of columns: x1, x2, x3, and y, right? So this y is nothing but image. This image will have some features like x1, x2, x3, right? And we are having 2D distribution of this image. Now, if you have 2D, you can easily show it on the xy plots. Suppose I have feature 1, I have another feature 2. What we have is, we have different distribution of this one. Suppose this is one of the image, another image, another image, or not one image. This is a collection of images. Basically, these are the collection of images. Similarly, these are also the collection of images. These are also the collection of images. Different images. Okay. Why there are distribution for feature vectors? Because see, suppose this is a bird. This is also a bird. But suppose this bird is different from this bird. This bird is a pigeon. This bird is a sparrow. They will be different in color, in shape, everything. When we talk about the pigeons, we are having different features again. Different features. We are not denoting the pigeons as single feature. Why? Because in the pigeon itself, there may be of different types of pigeons. It's possible, right? Correct or not, guys? Similarly, in a sparrow also, there may be different types, different colors of the sparrow. And that's why we are having distribution of these guys. Similarly, this guy is far away. Can you see here? This guy is far away. And suppose this is a picture of car and not a single car, different cars. And all the different cars will have different features. And that's why we are showing all the cars as a distribution of cars, not as a single element. Correct? What are the advantages of these features, feature vectors? What are the advantages? Okay, these feature vectors basically are used to tell something about some object. Here in our case, we have taken some image, right? So these feature vectors will define, will tell us that how they are different from each other based on these feature vectors, based on these features. So we are calling as vectors, feature vectors, because we'll be representing each one of the pixels in the form of vectors. That's why we are calling it as vectors. Okay, feature vectors. Now, just think that the advantages of these feature vectors, as we discussed, the main advantage is like these guys, these feature vectors are able to tell something about some data, some images. So these are nothing but the information basically. The features are nothing but information about some object. Okay, suppose I have a feature here, one feature, one of the features. Okay, I have another feature here. Okay, these guys are different. Suppose this is a say uh, boy 1 and this is boy 2. These guys are different. Why? Both are boys, both are humans, but again they will have some different features, and this distance between them will tell us how dissimilar or how similar they are from each other. Like in case of clustering we did. Remember, in case of clustering we used to have some kind of Euclidean distance, correct? And by using this Euclidean distance, what we used to measure using Euclidean distance, we used to measure the similarity. What is the similarity or dissimilarity? How two objects are similar or how two objects are dissimilar by using the distance measure. Similarly, use here. Okay. Suppose I have another. Uh, Similarly, I have some other features vectors for different things like bird or say animal. Okay. This is for say human y1 y2. Say this is for animal. Say dog 1 and dog 2. Now you can see the differences. These guys are here and these guys are here. They are totally different. They are large distance away from each other. But again, those two dogs are also some distance away from each other, and the two boys are also some distances away from each other. And that's why we are taking distribution here. They will be different from each other. Some features will be different. They will not be identical. In the same class, say pigeon and sparrow. We have two different classes here, pigeon and sparrow. If you look at one class, say pigeon, in this case, in the pigeon also, we are having different data, different features. Why? Because this pigeon will also be different from each other. All the pigeons will be different from each other, and that's why we are having these distributions. And all the feature vectors, all the different features are telling something about each one of the objects or pigeons or a sparrow or dog or boy, whatever. Okay, so these are my feature vectors. Now, talking about this machine learning versus deep learning here. When we have something called data, we have something called ML, ML algorithm. What did we do? We pass, after pre-processing, we pass the features. We pass the data, input data, correct, which will go through your feature extractor basically. That's what we do actually do, whether manually or by algorithms, right? And after that, it will give me output, correct? That's what we do, right? Input data will pass to a feature extractor. All the important features will go to the ML algorithm, and it will do some kind of job, like whether classification, prediction, or whatever, clustering, whatever it will do. This is in case of machine learning. But what happens in the deep learning? In the deep learning, our algorithms, whatever the algorithms we will use, they are so efficient, or they are so intelligent, that we don't need to provide these feature extractors. Okay, and if you don't need to provide these feature extractors, who will do? These algorithms are efficient enough that they will learn the features from the input data, and after learning the features, automatically by itself, it will take some decisions and it will give you the output. This is the main difference between your machine learning and deep learning algorithms. Okay. Now, representation. Again, I am coming back to the descriptors or features. Representations of descriptors or feature vectors. How will you represent? We discussed about some features in case of lion, right? We had some features of the eyes. This eye was having some features in the terms of pixels. Suppose this is the image of something, right? And all the pixels are represented in form of this matrix, right? Which is of size m cross n. Okay. Can we do something like, from this image, from this pixel value, I can take individual columns from here. This column, this column, this column, and all the columns from this image. These columns are nothing but all the pixel values 1, 2, which will range from 0 to 255. Correct. Now, all these values, all the columns, I am taking it like this one. And I am concatenating, I'm merging, I'm adding all these individual columns linearly like this one after the another. All the columns. We have a number of columns here. And after that, all the size, like sizes of individual elements here will be m, because we have m number of rows, right? And n number of columns. So the size of individual elements, individual blocks, this block, this block, this block, everyone will be m, because there are m number of rows here, right? When there are m columns, and finally the total number of elements will always be same, m cross n, m into n. Suppose I have, say, um, 2, 3, 4, 5, 6, 7, 8, 8 rows and 8 columns. So total it will be 8 cross 8. 64 different elements will be there, right? And what I'll do is, I'll provide these elements to the models or algorithms. It will go to my algorithms as features, different features of the images. That's what we used to do here. X1, X2, X3. We have 3 different features, right? And we used to send this X1, X2, X3 to the model. That's what we used to do there also. And similarly, we are doing here also. Same thing. We are basically flattening this thing, flattening this image into this form. Okay. Again, coming back to machine learning versus deep learning. So as We already discussed in machine learning, feature vectors are computed by some pre-processing module and then are fed into the model. Whereas in deep learning, raw signals are fed into the model and models decide which features to look for in order to classify the classes. Usually, these deep learning models are neural networks. Okay, so this information I have already given in a previous slide. Machine learning versus deep learning is clear. Now we were talking about this guy, representation of descriptors or feature vectors. How we will represent the descriptors or feature vectors. This is a representation. Given any image of size m cross n, we will represent all the features or feature vectors or descriptors in this form. Okay, this is the representation. Now we have something called discriminative and generative models. Okay, what are discriminative models? Suppose you have been given cat, you have been given dog, you have been given dog, cat, cat, dog. Different images of cats and dogs have been given to you. Okay, now this all these guys, all these pictures, they will have some features, feature values in terms of pixels, right? So I am representing all those feature vectors as xi. I will take 1 to n. It means 1 means this cat, 2 means this one, 3 means this one, so on and so forth. Okay, and we have to find the probability of x. What is the probability of x I? Okay, so that it will belong to some class called omega I. What is the probability of xi so that it will belong to some class called omega j or say omega k, whatever, different classes. Okay, we have to find the probability that these features will belong to any of these classes. That's what we do in the case of machine learning as well. If you remember the linear regression simply, okay, what is the probability of y? What is the probability of y given some feature vector x, some features x? Okay, and we have to find the expected value of y given xi, and this expected value is given by beta naught plus beta 1 x1 plus epsilon. Okay, so basically here also we are calculating the probability only, and here also we'll try to find out the probability also only, but in some different terms. There are many different concepts involved here, and we'll look into that. Okay, see, the overall learning of different things are same. Some few more concepts will be there, but the learning of machine learning or say deep learning algorithms, I mean, the learning is same everywhere, right? But the way we teach the algorithms will be different. How do we teach the algorithm in case of machine learning algorithms, or different algorithms in the machine learning itself? There are different working principles of different algorithms in machine learning and deep learning also. Okay, so we have to find the probabilities, right? And to find the probability, we have something called learning algorithm. We will pass these images, to our learning algorithms. Okay, when we pass these images, this data in the form of images to these learning algorithms, it will give me some output. What will be the output? It will give some output like predicted value. Okay, predicted value, right? Suppose we have some predicted value, we have some actual value here. So in case of machine learning also, we had actual value as well as we had predicted value. And when we have those two values, we can easily find the loss also. We can easily define the loss function as well. right? What is the loss? What is the error? And after finding the loss function, we'll try to minimize it, right? By using gradient. We used gradient in machine learning. So similarly here also we will use something called gradient. We'll find the gradient of losses. Means to minimize the loss so that our accuracy will be more and more, right? So this kind of algorithm where our learning algorithm discriminates based on probabilities, right? This kind of algorithm or model is called discriminative model. Okay. Second one is generative model. Okay. So suppose generative model says, this kind of algorithm says that what I cannot create, I do not understand. And this definition is basically given by one of the scientists called Richard Feynman. Okay. So what I cannot create, I do not understand. So first, to understand, I need to create something. And this kind of concept is called generative model. Okay. So to work on generative models, first we need to collect a large amount of data, large amount of samples from any domain, any domain, from any area. You have to collect a large amount of data first, and after that train a model to generate like it. Means you have to train the model. We have to train some algorithm to generate similar kind of data, and during the generation of the data it will learn something. This model, this kind of generative models will learn something while generating the model, while generating the data, like the past data, like whatever data you provide, it will generate the new data, and while generating it will learn. This kind of learning, this kind of models, this kind of algorithms are called generative models, generating algorithms, generative learning. That's why we are saying what I cannot create, I do not understand. Simply, I need to create something to understand the data. And that's why we are generating some models. Okay. There are few challenges in the deep learning. As you can see, here we have Taj Mahal. We have Taj Mahal. We have Taj Mahal. We have Taj Mahal. Taj Mahal. Taj Mahal. Taj Mahal. Taj Mahal. Taj Mahal. In each of the pictures given here, each and every pictures are of Taj Mahal only. But our naked eye will easily be able to recognize these pictures. But the problem is the computer. How will you learn? How will you teach the models? How will you teach the algorithms that these are the pictures of Taj Mahals, right? Because here you can easily identify the Taj Mahal, but here it can identify Taj Mahal as well as the birds, as well as the sun. Here it cannot identify the Taj Mahal easily because it's too dark. Here also it can also identify different trees, plants, etc. Lake kind of thing, something. Here also it can identify lake, river, or Taj Mahal as well. Here two Taj Mahals are there. The reflection. Here also, here also, here also we have the Taj Mahal, but we have some guy here. This is these are the challenges of deep learning. How deep learning will be trained in these situations. These are the very challenges, and we will impose some techniques through which we can overcome these challenges also in deep learning. So these are some of the challenges for learning, whether machine learning, deep learning, whatever the learning you say, these are the challenges for our computer to learn something from the data. This kind of data, this kind of scenarios given. Okay, and we'll try to overcome these challenges. Okay, now we'll talk about something called feature descriptors. Again, we'll come back to these guys, features. As discussed, these features descriptors are of two types. One is shape descriptors, another is boundary descriptors. Shape descriptors or boundary descriptors. and another is region descriptors. There are two types of descriptors in any given image. Okay, let's talk first about boundary features. Okay, of shape features. In boundary feature also, we can get or we can extract the boundary features by different methods. One of the methods is polygonal representation. Okay, another method is signatures. Another method is Fourier descriptors, and the final one is a statistical moments. We will look into each and every method in detail. How we can extract the features using polygonal representation, how we can extract the features using signatures, how we can extract the features using Fourier descriptors, how we can extract the features using statistical moments. We'll look into each and every methods in detail. Let's start with polygon representation. How we can learn the features by polygon representation, right? So firstly, let's take a closed boundary here. As I'll just draw a closed boundary like this one. Any boundary. This is suppose horse or zebra, whatever you say. Okay. And since we are dealing with digital signals, correct or not, guys? These signals, this boundary is nothing but we can also call it a digital. These are digital signals or discrete signal. Okay, these are discrete signals. Since they are digital signals or discrete signals, the points on the polygon or on the shape along the polygon, okay, all are discrete. Okay, so all these points on the polygon can be recursively divided into some arbitrary shapes. Like, since these points are discrete, we can have multiple points on the polygon, correct? And these are discretes, so we can divide the polygonals in different arbitrary shapes. Okay, so this polygon is not actually a continuous polygon, right? These are discretes because we are dealing with the digital signals, discrete signals in the computer, right? So these points are discrete. Now let's consider any two different points. So you have to choose two different points on the polygon at maximum distance, which will divide the polygons into two halves. So suppose this is one of the points and this is another point. Suppose I am just denoting as these dots, and these are my points. Okay, now just think I have polygon which can be divided into n arbitrary points in arbitrary shapes. Suppose I have taken two different points here. Okay, and these points are P and Q. Now after choosing those points which are at the maximum distances on the polygon, actually we are dividing the polygon into two parts, which is A and B, correct? So these are sub boundaries A and B of the polygon. Now just take the upper portion A part, okay, and draw perpendicular line from each point and check which point is at the farthest distance from this division line PQ. Okay, so I'll check that. So suppose I draw a perpendicular line here on this line. There are different perpendicular lines possible here, right? This one also, this one also. So what I am doing is I'll draw different perpendicular lines, and after that I am checking the longest line possible. It means I will take that point on the polygon on the upper half, which is at the maximum distance away from this division line PQ. Okay, fine. And I am naming this point as SR, for example. PQ, SR, AB. AB are the two different portions of the whole polygon, which are divided by the line PQ. And on the line PQ, initially I am considering the upper half. Okay, and after considering the upper half, from each of the points on the upper half on the polygon, I am drawing perpendicular lines on the line PQ, division line PQ, and I'm checking which perpendicular line is the longest one. It means which of the points on the upper half is farthest from this line PQ. And let's suppose this point S is farthest from the line PQ, and I draw a perpendicular line SR here. Now, after drawing this SR line, it will again divide the upper portion into two parts. Can you see that? This part and this part. Right? And now we have vertices of the above division. What are the vertices, guys? Can we see? This one. Right? This one. P, S, Q, and R. Sorry, P, S, Q, and R. Yeah, definitely. So we have one triangle here, for example, P, S, and Q. Right? By using this method, by further dividing this. Right? Now, what we will do is, as we did the division, first division, similarly, we'll find the farthest point from PQ, from this line PQ, same division line PQ, on the lower part of the polygon. Okay, and let's say this is the farthest point on the lower part of the polygon. This is my farthest point. There are different points possible here, right? So I am just assuming that this is the farthest point, and again I'll draw a perpendicular line from this point on this line PQ, division line PQ, and I am assuming this point as T and this as Z. So I'm drawing TZ line, perpendicular line on the division line PQ. Now, so up to this, we have found a polygon. Can you see that? Again, we will just add this P to T and T to Q. Now, can you see that P, S, Q, and T, we have found a polygon here now. This process of drawing a perpendicular lines on this PQ line can be repeated recursively, and we get many such points on the curve, this polygon curve, and finally we will get the polygon representation of the shape. It means this shape was some arbitrary shape. We did n number of divisions on this shape. We are having different points on the shape, and we are taking the perpendicular lines on the line PQ. And after doing that, we are having n number of shapes here, as you can see. And finally, after merging all the points, for example, next time we merge this point, this point, this point, this point, all these points, we are merging that, right? And after merging all these points, we will get the final polygon. Say P, Q, R, S, T, V, M, Z, O, L, K, I, Z. Suppose this kind of polygon I got. Finally, I'll get this kind of polygon from the shape. Right? Now, from this polygon, the final polygon, after recursively dividing the shape into n number of arbitrary points, and from each of the points, just assuming those points are the vertices, We will add all those points and finally we'll get this polygon. And this polygon will give you the different features, different boundary features of the shape by using some polygon properties. Okay. And this polygon will give you the different shapes or different features of the shape. Similarly, this individual vertices or small segments, what we have, say M, N, O, U, V, X, different vertices we will be having P, M, M, N, N, O, O, U, U, V, U, V, X, like that. So different vertices will also give you some boundary features. These small segments will also tell you something about the shape of the figure or image. So this is called polygonal representation of any given input signal in form of images. Next thing we will see, we can look at the signatures as well. So what are the signatures? So we can also get the features by signature of the shape. Okay, let's take some example. Suppose I have one square. Suppose I have one square. Okay, we can easily find the centroid of this square, right? From the centroid, I can have the axis, one of the axis, and this is another axis. From this point, from center, what I can do is I can iterate the points. From different points, I can join the centroid, and I can measure the value theta, the angle theta between this point and this line, horizontal line, axis. I can also say that this distance, what is the distance of this one? The distance will be d in terms of theta, angle. And after that, when you plot it, when you plot all the theta values with respect to your distance, when you plot the theta values with respect to distance theta, d theta, we have the y-axis here, we have the x-axis here, right? We have the zero angle, we have okay, let's see. So when you plot it, you will see that it is following some pattern like this one. And these peaks are nothing but 45 degree, 90 degree, 135 degree, and so on. This theta will vary from 0 degree to 360 degree. This will also give me feature of the shape. Okay, so this is the another way of getting the features from the boundary or the shape. So we can also get the shape of the boundary and boundary descriptors by these signatures. Okay, this is another way of obtaining the boundary descriptors or say features, feature descriptors or say safe features, safe descriptors, whatever you say, boundary descriptors, boundary features. This is one of the other ways to get the features. We can talk about something called Fourier descriptor as well. Okay, so these are all are correlating, as you can see. So suppose I have some curve, say this one, this curve I have, right? What do I need to do is this curve will have some location on the xy coordinate, correct? This curve. So after considering, we'll assume this as a shape in 2D space. Okay, and the space will have some discrete points. As we saw, this will also have some discrete points, right? When the shape will have some discrete points, let's take any point, kth point, say, just take some kth point, k. What did I do? We'll take any point K on the shape. Okay. And that point, this K point, will have two components. And those two components can be represented as complex numbers. We are talking in terms of Fourier. Okay. Fourier transformation, fast Fourier transformations. Okay. We can represent any point in the form of real number and complex number. Okay. So this point K can be given a function S, which can be represented as x of k plus j of yk. This one the real term, this is the imaginary term. So the points can be, all the points on this shape can be represented as Fourier coefficients. These are the Fourier coefficients. Okay, and all these points, okay, all these points will vary from this value k equals to 0 to n minus 1. Okay, so this is nothing but a kind of, Fouriers. In terms of Fourier, we are just converting those points in terms of Fourier functions, right? Now all these points, as I said, can be represented in terms of Fourier coefficients, right? Now we have this function sk equals to sk plus jyk, this function where k varies from 0 to n minus 1, right? Now we can take the Fourier transformation of these points of this function. Fourier transformation. How will you take this Fourier transformation, guys? We have a of u, this Fourier coefficient, equals to sk, this sk into e to the power minus j 2 pi uk divided by n. Okay, and we'll take the summation of this function from k equals to 0 to n minus 1. What is u? This u is nothing but Fourier coefficient, and u will vary from 0 to n minus 1 again. So the number of coefficients is equal to number of points on this shape. Okay, the number of Fourier coefficient for each of the points will have individual Fourier coefficient, right? And the magnitude of these coefficients, all the magnitudes of these coefficients give useful information about the shape of the boundary. Okay, now suppose I have this shape, I have this boundary, right? Now if I say what will happen if we take less number of Fourier coefficients, suppose here n minus 1 number of Fourier coefficients u are there. Now in some case, say I will take less number of Fourier coefficients. Suppose p number of Fourier coefficients I am taking. P is number of Fourier, not u. P is the number of Fourier coefficients, where p is less than n. N means number of points on the boundary. So p will vary from, again, 0 to n minus 1. Correct? Now this n value, suppose I am taking n is such that p equals to 2. I am taking only 2 points. So this Fourier coefficient au will take the value as u as 0 and 1. It will start from 0. That's why you're taking n minus 1, right? So we can take 0 and 1, only 2 points. Suppose I have this rectangle. The original shape is a rectangle. Original body is rectangle, right? Now we have the Fourier coefficients, 2 Fourier coefficients. We have to reconstruct the shape, okay, by taking the inverse Fourier transformation. So we'll take the sk, the shape. We'll take the inverse Fourier transform. How? This Fourier coefficients function into e to the power j 2 pi uk divided by n, and we'll take the summation form u equals to 0 to this p minus 1, and k will also vary from 0 to n minus 1. Suppose I am taking only 2 points, 2 Fourier coefficients. Okay, so these features, only by using only those 2 Fourier coefficients, it is not possible to reconstruct the original curve, right? So you may get something. Suppose this is the original curve, you may get something like this one. Suppose circle you are getting, not the entire square you are getting. And when we will reconstruct all the Fourier coefficients, we will get this entire square. Suppose I am slowly increasing this Fourier coefficients. What will we get? Suppose I got this kind of curve now. This kind of shape we are getting. Slowly, it has started to form the edges, minor edges, by increasing the number of Fourier coefficients. So you can see here, by using the Fourier descriptor also, we can extract different features of the boundary or of the shape of any given input image signal. And that's why we use Fourier descriptor as one of the features descriptor, one of the feature extractor in case of our deep learning thing, to extract the features, right? This is one of the feature descriptor. Similarly, we know polygonal representation, we know signatures, we know Fourier descriptors. Now finally, we have statistical moments. Okay, this is another way of getting some information about any shape. Okay, by a statistical moment, through a statistical moment. What is a statistical moment? We'll learn. Suppose again we have some shape here. Since we are trying to extract features about some shape, so every time we'll draw some shape. Right? Suppose again I am having some shape. Just take any 2 points on the shape. Suppose this point and this point. I am taking 2 points on the shape, P and Q. Okay, I am taking any portion basically of the shape. Okay, after doing the polygonal representation. So while doing the polygonal representation, we'll be having different shapes, right? As you remember, in the case of polygon representation, what we had, can you see here? This is the shape. Can you see? This one and this one is the shape. After we again finally divide, suppose this one is the shape, right? U and V are the shape, one of the shape. N and O, M, N are the shape, this shape or this shape. This is the shape. P and M are the shape, one of the portions from the given shape that we are considering here, like P and Q, for example. Right? Now we have what we will do now. We have this kind of shape, right here. What we will do here is, this is nothing but P and Q, right? So we are having this kind of thing. Okay, now it's better to do it from here. Okay, this one is the shape. Okay, now this is one of the axis, this is another axis. This is rotated in theta. This is having value of theta with the axis. Can I rotate these guys in this form? In x and y, and it will be having some value like this one. So, correct? So we will rotate the vertex of the shape in clockwise direction, right? With an angle theta. We'll rotate with an angle theta. And after rotation, we got it like this one. And then we can find the function of the shape. So this is the shape. This is the boundary segment, nothing but it will also have different points on the shape as discussed earlier. And this is nothing but boundary segment from the original shape we have got, right? From this boundary segment, what we can do is we can find the function of the statistical moment. And the statistical moment which is given by sigma k equals to we are having this ri here and ri distance and gri the function, and this statistical moment sigma k is given by ri minus mu to the power k into p times ri and taken summation for all I. Here mu is nothing but your mean, which is given by this mu is also given by summation of ri into pri. We have to calculate for all I. Okay. Now you can see here when k equals to 2, when the value of k equal to 2, this statistical moment will tell you about the spread of the boundary or shape. Spread of the boundary or shape. When k equals to 3, this value of k equals to 3, this statistical moment will tell you the symmetry of the shape. So by defining this statistical moment, we can also generate multiple information about the boundary or shape. We can have n number of statistical moment for each of the boundary segments taken, right? So this is another way to generate the features of the shape of any given boundary. Okay. So till now, what we did was we were looking at boundary features, right? And we looked at multiple methods, starting from polygonal representation, then signatures, then Fourier descriptors, and finally statistical moments. And we tried to extract multiple features by using those methods, right? Now, given an image, we have boundary descriptors and region descriptors, right? Boundary features and region features. Now, just think we have completed shape descriptor or boundary features. We will look at region descriptors now. Okay. So region descriptor basically can be of 3 types. We can, we can extract the region features by using 3 different profiles. Okay. The first one is called intensity profile. Second one is called texture profile. And the third one is called color profile. These are the 3 profiles which are used to get the features of the region. Okay. Now, first we will start with intensity. We will try to find some features. We will try to extract some descriptors of features by using the intensity. Here, just think this image. Some image has been given. This image has, this is the grayscale image basically, where we have only 2 colors which are black and white. Okay. Now, this image can be represented as a histogram. The intensity of this image can be given by this histogram. We can describe the intensity by using the histogram. Okay, we can plot the intensity of this image, okay, at different pixels by using this histogram. Okay. Now in this histogram, each color component has 8 bits. Okay, from 0 to 255. 8 bit means what? 2 to the power 8 means 256 is 0 to 255. Okay. Now this histogram is nothing but we can uh, give the histogram, write the histogram in the function hi equals to ni, number of points. We can normalize this histogram also. Okay, suppose the values are ranging from 0 to 255. Okay, now we can normalize this histogram. So the normalized histogram hi can be given as ni upon n. The pixel values, each pixel values divided by n. Okay, so n is nothing but total number of pixels and I is nothing but intensity value ranging from 0 to 255 for each of the pixels intensity values. Okay, so when the value of the intensity, say intensity value, say I, at any point at any pixel is 0, the pixel will be darker. It means fully black. And when the intensity value is maximum 255, it will be very brighter. It means white. Okay, and this intensity actually varies over the shape, over the region. This intensity values varies over the shape. As you can see here from the given picture itself, you can see that the intensity of this one is very low, as well as the intensity of this portion is relatively higher. And so we saw that, see, these are higher values which correspond to this portion. These are very lower values which correspond to this portion. These are mediums which correspond to this one. Okay, so these are the distribution of your intensity over the image. And this distribution is given by this histogram. Okay, now as I mentioned, when the value of intensity is 0, it will be darker. When the value of intensity is maximum, it means 255, the image will be brighter or white. This intensity is varying within the image. It varies over the image or over the region. And this variational intensity is given by your statistical moment. Again, sigma k. And it will take the same form, like Ri minus mu to the power k into h of Ri, histogram value, h of Ri for all I. And this mu again will be given as summation of Ri into Hri for all I. Okay, so this variation of intensity is given by this function, statistical movement. Got it? Is it fine, everyone? We are talking about the intensity. Okay, and the intensity varies over the region, and this variation is given by some function called a statistical moment, which is given by r summation of Ri minus mu to the power k into Hri. And this mu is nothing but your, this one h is nothing but your histogram values. Okay, this intensity, suppose we have some image, this kind of image. This is brighter as compared to the previous image, and the values of this image can be represented, the variations of this image, pixel value variations of this image can be represented again by some histogram. And you can see the relatively higher values, which means the more and more higher values are there as compared to the previous one. And so because since this image is brighter as compared to the previous one. Okay, similarly you can have this kind of value. From grayscale we have RGB image, means colored image. This variation can also be given as in the three forms: R, G and B. RGB. This variation can also be explained using these three forms. RGB, here each of the pixels will vary from 0 to 255. R, G and B. Now you'll ask me, why only three? We have this cream color, we have this white color, right? So by combination, by combining these pixels, like what is the pixel value of R, what is the combination of the pixel values of R, G and B, which will yield this kind of color, this combination. So for this combination we have all the three values of R, G and B. Whatever the values of pixels in this region, this will be taken by these values, right? RGB, correct or not? So these are given by this histogram. And again here also we will take the variation, we will calculate the variation by using some function which is called a statistical moment. Okay, similarly we talk about this one, intensity. Each color component has 8 bits ranging from 0. This is the summary that in the slide. Each color component has 8 bits ranging from 0 to 255. Okay, histogram HI is nothing but NI, and this normalized histogram is nothing but HI equals to NI divided by N. Okay, there's the same thing, repeating thing in the slide. That is for your reference. Okay. Now the next thing is texture. Okay, what is texture? So basically it is not possible to define the variation of a texture in any given image by any formal definition. Okay, there is no definition for texture here in any book. So if they give, there is not formal definition, exact definition. Every different book will give some different definitions of the texture. Okay, so I'd rather say there is no definition. So this kind of variations in the image is called texture. Okay, suppose this texture can also be represented in form of pixels in a matrix. These are individual pixel values. These are individual pixel values which are in the form of matrices, rows and columns. Each value here will give you pixel values, which will range again from 0 to 255. Okay, and this 255 values can be given here. So here in the texture also we can do the similar kind of things. We can extract the information of the texture as well. We can extract the information of the texture in the form of pixel values. So this texture also can be represented in form of matrices, and we can take the decisions how your region is described by some features called texture, how your region is described by some features called intensity, how your region is described by some features called color profile. Okay, so color is nothing but that's what we already studied, the color thing. Here the same thing, color. Okay, what is the color? The pixel values, color. Intensity, by using those colors, what is the variation of those colors which will define your intensity within any given image? That is called intensity. Similarly texture also. Okay. So these are the values, guys. These are the three different region descriptors in any given images. So there are basically two different feature descriptors. One was shape descriptor or boundary descriptor, another is region descriptor. In the shape descriptor or boundary descriptor, we study about four different methods. In the region descriptors, we are interested in intensity, texture, or color. Okay, by using those features, by using those information from the image, we can take some certain decisions. What kind of image it is, we can analyze deep into the images, we can analyze the very deep truth about any images given image signals. Okay.